So here are a few more examples that you can solve on your own. I'm just going to explain those examples are. So again, this is very similar examples as before, but the only difference is that you have incoming flow rate and you have outgoing flow rates with a different concentration of contaminants. But then there is also another outgoing, which is evaporations. But it really doesn't really affect the mass balance equation for pollutants because you can assume that the contaminants are not evaporating from the systems. So that would be C, evaporations would be 0. If you do that, you can write the mass balance equations. There are a couple of things given over here. There is a reaction term, which is given here, that's first order. And then volume is given, K is given, effluent concentrations is not given. That's something you have to calculate. C is given, which is 6 milligram per liter. Q upstream is given, which is 9 times 10 to the 4 meter cube per year. Q downstream is given, which is 8 for meter cube per year. Q evaporation is given 1 times 10 to the 4 meter cube per year. The only thing that's not given is C downstream. And this is a steady state. It's written here. Then you can solve for the equations. Again, steady state, the very left side term is 0. Q in, C in, minus Q out, C out would be the reaction term. So this is here, volume times the Kc. That's because of first order reaction, as you see over here. Sorry, this is first order. Now if you write all the terms, so that would be Q in would be Q river times C upstream. Q out would be the very first one is the downstream, Q down times C down. Again, we can make the assumption is C, what is in the pond is same as C down. So you can write C out is C. Then the evaporation, you know the concentration of evaporation is 0, so that means you don't have to write that term. So even you write Q evaporations times C evaporations, this term is 0. Then minus K P C. So if you solve for C, you get Q river times C upstream divided by Q down plus K V. And you can solve for it because every other equations or terms are given. Just ensure that the units are similar on both sides. The next example, as you can see from the illustrations, your incoming flow rate and concentrations are given. Your outgoing flow rates are given, but not concentration. That's something you have to calculate. That means you need to know the volume of the lagoon as well as the rate constant. So rate constant is given 7 per day. So that's first order. And the volume is given. Lagoon surface area is 10 hectare. Depth is 1 meter. So that means you can change to volume, which is area times D. Just have to ensure that hectare to convert that into meter square. Once you get that numbers, then you know the volume as meter square, meter cube. So that's number would be in meter cube. So you know the volume, you know the rates, everything else is given. You can derive the mass balance based on the previous equations that we derived. and then you can write the final formula, which will be exactly similar to this formula. So that would be C fluent would be Q in C in divided by Q out plus K volume of lagoon. Third equations or third examples is a little bit different because it's on steady state. So if you see over here, if you write what's given here is what's the concentration of a benzene in a pond with volume 1000 meter cube. After a week, if 100 gram of benzene is spilled into the pond, assume benzene is decayed in pond at a rate of 0.1 per day. So let's see what's given. The volume is given. There is a pond. That volume is given, which is 1000 meter cube. If you write in terms of volume in liter, so that would be 1000 meter cube. 1 meter cube is same as 1000 liter. So that's become 1 million liter. And you also have to know what's the initial concentrations. That's not given, but you know how much amount of benzene is added to the pond. So the mass of benzene is 100 gram. Volume of pond is given 10 to the 6 liter. So if you calculate the initial concentration, so time t equal to 0, that would be amount of contaminants mass over volume. But if you change that to milligram, that would be 1 gram is 1000 milligram. So that become 0.1 gram per milligram per liter. Now let's write the mass balance. On the time half is after 7 days or a week. And K is given 0.1 per day. So that's first order. So if you write the mass balance equation for any pond, because you know what's the inflow outflow, then you would have written for this. Again, this is not a steady state, so that means you cannot cancel that first term. So that's P dC over dt of the system would be the first term with the flow rate. What's coming in? There is nothing coming in, so that means you can write 0. What's leaving the system? Nothing, so that's 0. Then the reaction term, so that would be plus volume time Kc. That's because first order reaction. Negative because reaction decreases the concentrations. So that means what you got, volume cancel, dC over dt is minus Kc, which you can solve. dC over C equal to minus K dt. Initial is C0, then it becomes C at time t equal to 0 at certain time t. You solve that, ln C, C0 by C minus K dt. I'm sorry, this is dt. Integration is just t, so that would be ln C minus ln C0 is minus kt. Ln C by C0 is minus kt. C equal to C0 minus kt. So that's the equations. So if you write this number, C equal to C0, which is 0.1 milligram per liter, times e to the power minus k, k is 0.1 over day, times time equal to 1 week, so this is 7 days. Cancel. You got the number 0.1 milligram per liter times e to the power minus 0.7, whatever that number would be in milligram per liter. So that conclude all the examples that we have for this class.